So I'm going to talk about oscillating neural networks. So maybe I should introduce myself. My name is Siegfried Karg from IBM Research in Zurich. And I'm standing there as the only author, but of course, this is not only my work that I'm going to present today. And at the end, I will acknowledge also the students that have basically done most of the work in the lab. And okay, oscillating neural networks are a neuromorphic computing approach. So computing with oscillators or oscillations, the idea stems from rhythmic brain activity, so-called brain waves. Neurons fire synchronized, and the brain is using these for a lot of functions that are very basic functions. And so we try to mimic, or one tries to mimic those brain activities using oscillating neural networks. So the neurons, these are the oscillators, and then the synapses are coupling the elements. And these coupled oscillators have an associated memory, and that is, you may have seen those metronomes being coupled on a skateboard or on a platform, and you can initialize them randomly, but after a couple of minutes or a couple of seconds, they synchronize. They synchronize in frequency, and they synchronize in phase. So that's the first idea what an oscillating neural network can be. But of course, you need more. And so you need, of course, you need oscillators, and then you need to couple them. And while on with the skateboard, you cannot tune the coupling. But for oscillating neural network to do useful computation, you need to have individual couplings between each oscillators, and these should be tunable. And we are using electrical oscillators, and the tunable elements, these will be in the end, so tunable resistors, that will be memristors. So, and that also already you see from this, they should be integrated. So they should be closely together. And of course, we are coming from IT industry, so we want to have this all on silicon. And so if possible, integrate everything on a silicon, if possible, in the back end of the line, so you have the underlying silicon circuitry, and then you have metal layers on top of that, and then on the very top, you add the memristors and the oscillators. The oscillators I will talk today will be made of a metal insulator transition material, vanadium dioxide. We have heard already yesterday some talk about that. And I will not focus on the coupling too much, but the idea is that this will be memristive type of material, so resistive RAM materials. So what does an oscillating neural network do? Why is it interesting? So, okay, it's a variant of so-called Hopfield networks. That's a physical network that is based on energy, and so there are stable states in this network. So you can program these such that we will use the phase. So some of these oscillators we want to have being in phase, and on some of these oscillators should be out of phase. And when you disturb this network, it will always fall back into one of those stable states, something that you programmed into it. So here in this sketch, so each oscillator is a pixel, and you want to have, let's say, all those which are now in blue being in phase, and the other ones out of phase. And so you set your coupling matrix such that those, and I can tell you later on, so it's a simple learning rule, it's Hebbian or Storke learning rule, it's a simple algorithm. Basically what you do is and you can, if you disturb your network, it will always find back a way because it's an energy minimum, and you can have multiple energy minima. You can program not only a T, but you can also program an S or an X. And the larger the network, the more patterns you can store. And so there will be more energy minima, and if you disturb here, it will fall back into the closest local minimum. So how do we do the oscillators? So that's my material part of research, where I'm originally coming from. I'm a material scientist, using vanadium dioxide as oscillator. So vanadium dioxide, there's a insulator to metal transition at about 68 degrees. It changes from monoclinic to a rutile structure as a function of temperature. It's as we have heard yesterday, it's a first order transition, and we trigger this transition by Joule heat. So it's triggered by heat, and we will build devices, very simple devices. So it's just a stripe of vanadium oxide and 2 metal electrodes, run a current through this, and while we run the current through this, as soon as it reaches 68 degrees, it will switch from a higher resistance to a low resistance. You can also do this in a crossbar fashion, where we have a bottom electrode and a crossed top electrode in this, the vanadium oxide in between. Typical IV characteristics, depends whether you drive it in with voltage drive, then it will jump vertical in current, or if you drive it with constant current, then you get these typical S-shaped structures. And so this is then the basic circuit of an oscillator. It's just your vanadium oxide device resistor in series with a load resistor. So when you apply a DC voltage here to these series resistors, when the vanadium oxide is in the insulating state, the voltage drops mostly across the vanadium oxide. There is a small current going through that is Joule heating, so it heats up. At a certain point, when this is switching to the metal, then this becomes quasi a short, and now your voltage drops here across the series resistance. But this means also then, because the voltage drop is low here, it will cool down. So there's no power burn anymore, and it will cool down, and as soon as it is below the transition temperature again, it will switch into the high ohmic state, and it starts heating again. So you apply a DC voltage, but this thing will oscillate. If you measure the voltage here at this point, this will oscillate. We will add another capacitor, which is not strictly necessary, but of course in practice there always will be some parasitic capacitance, and we'd rather put in there a capacitance that we know, then we can control it. It also has practical reasons for our circuitry because we have limited time resolution. So one issue with our vanadium oxide resistors is, and I should go back here, we use it on silicon oxide. And on silicon oxide, we don't get a epitaxial layer of vanadium oxide as if we would do this on a sapphire substrate. You get granular polycrystalline material. And that means you see also there's edge roughness, there's surface roughness. There is a limited number of grains in there, and the smaller you make your device, the more variability there will be. And this variability is an issue for us. And to overcome this variability, we use a technique which is called harmonic injection technique. So we replace our resistor that we had here with a transistor. So the transistor is just there to set a conductance, to set a resistance for this. But you can use the gate to tune the resistance. So for us, it's just a tunable resistor. But it has the ability to also superimpose an external frequency. So what we do here is, so if we apply a constant gate, so we have a constant resistance and we have the oscillations of our circuit. And if you do an FFT, you find that the natural frequency of this particular oscillator is a little bit less than 5 kilohertz. Now we superimpose on the gate voltage a 5 kilohertz oscillation. And you see that from the pattern of the oscillation, the vanadium oxide oscillator reacts to that. It changes a little bit the form, and if you look at the Fourier then you see that now the frequency is exactly 5 kilohertz. So we can tune the frequency of a vanadium oxide oscillator with an external, with the harmonic injection. So this helps us to stabilize and synchronize later our ONN, because if every oscillator has a slightly different natural frequency, it will become difficult to couple them all to sync into one frequency. That will, if we help them with this external frequency, then it will be easier to couple them, as we see later. And that's what the experiment that we did. So in green, that's the natural frequency of this oscillator, and then we can modulate, we can tune the gate frequency in a certain range, so 3.5 kilohertz to 6 kilohertz in this, and our oscillator will follow. If you tune too much, then we lose synchronization, and then the oscillator will oscillate with its natural frequency again. So now, how do we couple oscillators? So we start with a very, very simple scheme. We just use a tunable resistor here. So this could be our memristor. And so we switch on the voltage for both oscillators at the same time, and we can then achieve these two configurations. So we have an in-phase oscillation if the coupling resistance is small, so that means strong coupling, and we get them out of phase if we have a larger coupling resistance here. So this we can tune. So we can tune the two oscillators with the coupling strength that we apply. So let's do our first pattern recognition experiment. So that will be our first computation. So we have 3 coupled oscillators. They have all the transistor that is in series, and we have 2 trained patterns. So we want to have those 3 oscillators where oscillator 1 and 2 are in phase, and the third one is out of phase. That's one pattern that we would like to have stable. The other pattern is the first oscillator is individual, and then 2 and 3 are in phase. So these are the 2 trained patterns. So we set the coupling resistance accordingly. So okay, you can do an educated guess how you have to change how the ratio between the coupling resistance has to be, and then we use a second variable. So we have the coupling strength as one parameter, but the timing, when do we exactly switch on the voltage that we apply to each of the vanadium oxide oscillator? So this is our second variable, and that's our input. So if we want to input a, let's say, white pixel, we apply the external voltage at time 0. If we want to implement a black pixel, we apply the external voltage to this with a delay, and the time delay, which is about half of the period of the oscillations. And the gray pixel then is, you can imagine some timing in between. So in this example here, we apply the second pixel at a time delay which is close to 0. And after a couple of oscillations, then the first and the second oscillator, they will go in sync. They will have in phase, while the third oscillator stabilizes at a time with half a period in between. If we use the same circuitry, same coupling resistance, but just vary the timing, the input. So we input now a dark gray, so meaning that our second pixel has a time delay which is closer to tau or a half. And then after a couple of oscillations, then the middle pixel and the right pixel, these two will go in sync. So that's our first experimental pattern recognition. So we have an input which is a gray pixel image, and the output is one of the 2 trained states. Okay, so as I said, we have issues with the variability of the pixels. So we would like to do larger networks than not just the 3. But that is in practice that is difficult because the variability of our oscillators is too strong very often that we have to have a hard time to find in one array 3 or more than 3 that are exactly the same frequency. So we use our harmonic injection technique also then for the coupled resistance. So we can use the same trick as we did before, applying an AC to the gate, and that improves our synchronization window. So without the harmonic injection, we can only synchronize the 2 oscillators if they are more or less exactly the same, while with the harmonic injection locking, we have a much wider space here in terms of frequency, and this allows a wider window. And we do another trick. We can not only use a memristive coupling or a resistive coupling, we can add a capacitive coupling. The capacitive coupling so while the capacitive coupling pushes the phase apart, the resistive coupling, if we low resistance, pulls it together. So if we set the capacitor as a constant, that tends to push the oscillation, the phase apart, and then we pull it together with this. And so to use harmonic injection, actually here we use second harmonic injection locking, together with this RC coupling, we get in this experiment here we have 2 memorized patterns, while in the typical case, one of those patterns one of the oscillators will probably always fail. But when we do the RC coupling, then we can very stably get the 4 oscillators to work and do a 4 oscillator experiment. So that's the sketch. So if without the RC coupling, we have a very low parameter window to reach the out of phase configuration, while when we do the RC kind of coupling, then the out of phase we can increase the parameter space, and it's much easier than to couple. So a couple of simulations that we did is what we could use an ONN4. So and the example that we show here is we want to use a convolutional neural network, which is typically used for image recognition. And here you have a set of filters, a set of kernels that you're sliding. So it's a small set of typically 3 by 3 pixels that you're sliding across your image, and you try to detect patterns. So we want to replace such a filter with an ONN. And in our ONN, we can program multiple of those features in one ONN. And what we have done is we were using edge detection filter. So we did unfortunately I missed the slide, so that I have to explain by hand. So we had programmed a vertical, a horizontal, and 2 diagonals into one ONN with 9 pixels. And then we were sliding this across using MNIST handwritten digit database, and then one of those 4. Actually, there's also a 5th one, which is if you don't find anything, and you will find, and then you can use this one ONN instead of 4 kernels to find image, the edges of your filter. We have also proposed another. It's also based on convolutional neural network, but it's an intrusion detection system. So intrusion detection is, if you have an intranet, you want to make sure that whoever enters your intranet is also authorized to do so, and is not some intruder that wants to steal your data or whatever. And so that is in each for each router, etc. This is something you need to include. You require fast inference. It's power sensitive. and it requires only infrequent training, so only if there is a new kind of virus, a new kind of intrusion scheme discovered, then you need to retrain your. And so this kind of network would also be, we think, ideal for an analog ONN scheme as an example. And then finally, we propose a multilayer ONN cascading multiple ONNs and using our scheme with the harmonic injection locking. So the output of one ONN is a harmonic signal, and we want to feed this into the second layer of an ONN. And with this, we will hope that we can do more complex neural networks. So the conclusion, I hope that we convinced you that ONNs are a powerful tool for doing computing. The VO2 oscillators, they are a viable option. So they are scalable, low power, high endurance, and integratable with silicon technology. These are the prerequisites that we require from an oscillator, and we need to also integrate them with silicon, and we need to integrate them with memristors. I've showed you the injection locking technique to overcome some variability issues that we have, and I've proposed pattern recognition based on trainable ONN for convolutional neural networks. And then finally, the acknowledgements that for the people who really did the work, so Nele and Olivier, Elisabetta and Bernd, and also I would like to acknowledge our funding sources which are 2 European projects, Manic and Neuron. And last but not least, I would like to thank my colleagues from the IBM Binnig-Rohrer Nanotechnology Center, which help us to make the devices and fabricate and the materials and optimize. So they spend a lot of time with us. And I thank you for your attention.
Thank you very much for this great talk.